Hello, everyone. Today we have now the first session of analog and mixed signal, and we have around 10 to 15 minutes delay because of the panel discussion. So let's start the session. Welcome to everyone. And this is the first session of the paper presentations in VLSI conference. But before that, we have an invited talk by Dr. Dhireesha Kudithipudi. So title of her talk is Cheetah 2, which is automated framework to identify low precision numerical formats for DNN accelerators. But before that, I would like to give a quick introduction about Dr. Dhireesha. So she's a senior member of IEEE and currently a professor and funding director of AI Consortium at the University of Texas, San Antonio, US. And she's also Robert F. McDermott Chair in Engineering. So her team has developed comprehensive neocortex and cerebellum-based architectures with non-volatile memory elements, hybrid plasticity models, and ultra-low precision architectures. So she is very passionate about the transdisciplinary and inclusive research training in AI fields. So her research interests include neuromorphic AI, low-power machine intelligence, brain-inspired accelerators, and use-inspired research. Dr. Dhireesha was the recipient of the Claire Booth Luce Scholarship in STEM and 2018 Technology Women of the Year in Rochester. So we move ahead with Dr. Dhireesha's talk. Thank you.
Hello, welcome all. Thank you for joining us today. I would like to thank Professor Maryam for the invitation to present at the VLSI Design Conference. In today's talk, I'll be discussing about identifying low precision numerical formats for DNN accelerators and some of the work we have done in building an automated framework. This work is in collaboration with my students Hamid, Vedant, and Paige. Hamid has been the lead author on this specific research. So before I go into low precision arithmetic, I just wanted to give you a brief overview of what my research lab focuses on. We are interested in designing the next generation computing systems that can perform natural tasks. And what I mean by natural tasks here is tasks that require human intelligence. And we would like to solve these in the most energy efficient way. And in order to do this, we take really a multidisciplinary approach. We have 5 research thrusts, core thrusts that we are focusing in our research lab currently. One is particularly looking at neurally inspired algorithms, whether they are spiking or rate-based. The others are focused on lifelong learning algorithms, particularly designing algorithms that can learn continuously through their lifetime, either using plasticity mechanisms that we observe in the brain or using some kind of dynamic learning. And we achieve energy efficiency not only by the choice of algorithms we are making, but also by using mechanisms like model compression or circuit and architecture optimizations that could help us in achieve further savings. And today's talk really falls in this research thrust, where we are looking at model compression, or particularly low precision arithmetic in order to get that model compression. We also do the hardware design of the algorithms we are developing using memristors or CMOS digital and mixed signal design implementations. And we collaborate with researchers who are experts in photonics or FEFETs in kind of seeing if our architecture scale to some of these other technologies. But really looking at this, you can see that it is not possible for any one group to solve all aspects of these problems. So our collaborators play a key role in how we are building holistic solutions in this space. So coming to low precision arithmetic, let's look at why it is important to really look at low precision arithmetic. If we look at the memory requirements today to train the AI models, they are typically several times larger than the number of parameters that we have in these models, billions of parameters, and that's growing significantly. So that's what you see on the plot on the left for all the developments that we have seen in the machine learning world with all the popular algorithms and the number of parameters that these algorithms have. And you can see that it is growing significantly. And the transformer, one type of algorithm where the memory size or requirements have grown 240 times in 2 years, whereas the AI hardware memory is growing at 2x rate. And if you look at the right, it kind of shows for the similar set of algorithms what is happening in terms of the computational requirements, particularly the training requirements for these algorithms. You can see again that the training computation time in petaflops, it's growing significantly, like with the wave 2 vector that you see or the BERT models, it is significantly high. Whereas the computational scaling that we are seeing is not meeting these requirements. So there is a significant gap that you can see. This is not just a requirement to keep the energy and compute expenses low, but in general, it's a concern if these requirements grow at this pace, right? There has to be definitely improvements at the algorithm level, but there also have to be improvements at all scales of abstraction once algorithms are transferred onto the hardware. So one solution is to compress the models, right? Like instead of using, and there are several compression techniques, several quantization mechanisms that are used in order to reduce the model size. So with the ideal model choice, we can save almost 100 times in both compute and memory if we do the right compression mechanisms. So the typical ones, like for example, instead of using a float 32 for your multiply and accumulator unit, you could use a float 8, and this could reduce the memory footprint, latency, and the energy consumption. So these savings that you get because of quantization or pruning approaches can be highly beneficial. But there is a challenge, right? Well, if I reduce the model size from 32 bits to 8 bits, what happens? The side effect of such quantization is usually there is a degradation in the model accuracy. So the precision that you have for a 32-bit floating point is obviously significantly higher than an 8-bit floating point. So then which type of numerical formats should you choose in your implementations? So if you think of this as a question as to what is an appropriate choice, it is really dependent on the task you're trying to solve, as in whether the task requires high precision solutions, whether there is an opportunity to have energy accuracy trade-offs in your design, and whether the precision, whether the numerical format that you're choosing can support non-uniform distribution, and whether it supports variable precision. And this plot on the right shows experiments that are done on AlexNet with Cypher10 with varying fixed point, binary net, floating point, different types of numerical formats and bit precisions to see how it impacts the classification accuracy as well as the energy consumption. You can see that the top, where the floating point 32 32, you get the highest accuracy, but also the energy consumption is really high. Whereas if you get to lower order bits, you get like some kind of sweet spot for accuracy and energy consumption. So what are the typical numerical formats that are used? Our fixed point is a good choice because it is hardware friendly. Where here in this equation, Fs represents the fractional bits, S represents the sign, and because fixed point is hardware friendly and it supports uniform distribution, it can be used in model compression, but the price you pay often is the performance degradation. So researchers have come up with ideas like tapered fixed point, where you could have non-uniform distribution in this format, unlike fixed point, and it is hardware friendly, and you could use unary encoded integers in this case. But the main difference is the integer part being that unary encoding, and SE is the scaling factor here. So it's really good for non-uniform distribution, but there is still a challenge in a sense that the dynamic range that you get for this tapered fixed point is lower than the float. And on the right is the floating point, which again supports non-uniform distribution, and it is high power, high energy solution in a lot of cases, and it has fixed length. And here in this equation for float, B is bias to shift the exponent. And there are two other formats that have recently been garnering a lot of attention in the community. And we have published some of the early work as to why this numerical format is beneficial for deep neural networks. And if you see on the left, we call this numerical format POSIT. It has both regime part and unary encoded part, that the encoding needs additional decode and encode, and because of that there is additional complexity, but you get greater flexibility with POSIT in terms of the precision depending on where your parameters are concentrated for your deep neural networks. And there is another slight variation of POSIT called generalized POSIT, which adds two parameters to make it more flexible, RS and SE. SE is again the scaling factor to make it flexible, tapered precision, and improve the dynamic range. So in POSITs, this K that you see here is the regime value. ES is the number of exponent bits, and E is the exponent value, and FS is the number of fraction bits, similar to fixed point. So we have all these numerical formats, and we have several research articles showing the benefit of choosing different numerical formats. So the challenge really is, how do we identify the optimal optimal numerical format for a DNN accelerator? There is an incompatibility in the accuracy and hardware complexity trade-offs, and the search space can grow significantly large. And you can see here the number A, 3 times 4 power 50, which is significantly large when you're thinking about choosing the right numerical format and bit precision for a network. And the hardware constraints themselves change from edge device to device. An Apple A12 versus an ARM M7 might have very different requirements. So what we try to propose here is an automated framework to identify the low precision. So we call this Cheetah 2.0 because we proposed an earlier framework with fewer features, but in here what we're trying to do is use integer linear programming optimization to help us identify the right numerical format and subspace choices based on what the user wants. So the user can choose the design constraints, and if you look on this cartoon here on the top, the user constraints or the interface that you see is being fed into the framework that kind of sets this ILP optimization with all the design constraints and kind of gives us different options for the DNN models. So it supports 5 numerical formats, 3 data flow approaches, and 5 processing element configurations. And we kind of assess the suitability of the formats based on these 8 different metrics that you see here: energy, power delay, EDP, frequency, and also the... So here is an example of how we evaluated using the Cheetah 2.0 framework. For example, we have a deep neural network where we want to analyze in the 5 to 8-bit precision range, and particularly interested in seeing how generalized posit numerical format fares. We can have the setup and evaluate the performance of all the 5 numerical formats. The ILP optimization is triggered. It can minimize or maximize objectives based on the what we have for the X-chain here. So for example, you can maximize the accuracy with respect to constraints on EDP and power, or you can maximize for power and so forth. And we've analyzed this on 5 different PE configurations and 3 data flow arrangements. And all the MAC units that we have within this PAs were synthesized using the SAED 32 nanometer technology. We tested it on 2 different benchmarks: keyword spotting and image classification. For a 32-bit format, it had 92% accuracy for keyword spotting, and image classification had 86% accuracy. So this kind of diversity in the DNN models, one is ResNet 8 and the other is the TSCNN. When we evaluated it across the 5 numerical formats, we see that generalized posit performs really well for 5 to 8-bit precision. So if accuracy is of top priority, you could pick that numerical format. And the second best is posit in this specific context. And you can further analyze your results in much more detail from the information that is spewed out of Cheetah 2.0. On the left, you can see plots, for example, for image classification task, and we want to find the best accuracy with energy delay product on the top with the accuracy constraints. And the value that you see in this GP80 is what the Cheetah is providing as the ideal format for this specific task. And here GP is generalized posit, and 80 represents 8 bits and 0 exponents. So this is just an example of how you can use this with different constraints, and detailed analysis is provided by Cheetah to kind of make the right choice. And if you're, like, for example, looking at more frequency and accuracy, you can see that a different numerical format is highlighted as the optimal choice. But consistently across both the tasks, you can see that generalized posit with 8 bits, whether it's a 0-bit exponent or a 1-bit exponent, is identified as a good format. And similarly, we've done experiments with memory utilization and power. So these are just examples, and there is extensive analysis that we could do with Cheetah 2.0. So in summary, we kind of developed a low precision hardware software co-design framework to choose the right numerical format. And this is a great tool for early stage design space exploration. We are hoping to release this in GitHub very soon. It is going to be presented at Conga workshop, and most likely we'll be releasing right after that. So some of the interesting findings are that generalized posit yields about 25% improvement in the average inference accuracy over other numerical formats. So it could be a good choice for some of these edge devices. And the ILP identifies the optimal numerical format in less than a second. So it's pretty fast, so compared to reinforcement learning based approaches. So it's a great early stage design space exploration tool for identifying the right numerical format for the DNNs. And we would like to acknowledge Dr. John Gustafson, who is actually the inventor of posit, generalized posit, and tapered fixed point. We had several discussions with him over the years. And you can see some of the pictures here with John there holding up the glass on the left with my students, and the other one is when he was at Singapore. Thank you all so much for joining me today. And if you have further questions or if you're interested in PhD opportunities, feel free to reach out to me at the email address provided on the screen.
Thank you, Dr. Dhireesha, for the exciting talk and specifically bringing the notion of the POSIT and also about the integer programming and optimization based on the user constraints to find the optimal precision. Actually, it's a very interesting point because this is really something which has a severe trade-off with the energy efficiency. And energy efficiency now is a very important part and cannot be compromised by increasing the precision. So it's a very interesting and hot topic of interest to the community. And because we have delays, so we move on to the paper presentations. But if you have any question, feel free to directly write to her, as she mentioned, and therefore you can directly interact with the speaker. So we move on to the paper presentation session, and we have the first presentation in this session, which is a 5 Gbps PAM4 voltage mode transmitter with current mode, continuous time linear equalizer, and which will be presented by Shraman Mukherjee.
Hello everyone, this is Shraman Mukherjee. Today I'm going to talk about a 5 Gbps PAM4 voltage mode transmitter with current mode continuous time linear equalizer. In this slide, we'll talk about the outline of this presentation. In first few slides, I'll discuss about the motivation of our work. Then I'll describe the proposed transmitter architecture, followed by the measurement results, and finally I'll conclude this presentation with a summary. This figure shows the conventional wireline transceiver. As we can see from the figure, the transmitter employs output driver with embedded 2 or more taps of FFE. The transmit side feed-forward equalization suffers from supply-limited output swings. Therefore, an automatic gain control block or programmable gain amplifier is required at the receiver side, which is before the equalization by the CTLE and digitized by the ADC. Now, in this slide, we'll talk about the cons of 2-tap FFE with AGC. This equation shows the transfer function of 2-tap FFE. As we can see from the equation, the DC gain reduces with the higher equalization, as the DC gain is proportional to 1 by 2 alpha minus 1. Here alpha is the equalization coefficient. As the equalization coefficient reduces, it means higher amount of equalization. With the higher amount of equalization, the transmit swing reduces. As the transmit swing reduces, we need higher amount of gain at the AGC block. The higher amount of gain means higher power consumption from the power supply. Moreover, higher gain of AGC introduces nonlinearity and thermal noise into the system. This figure shows the design example of PAM4 transmitter with feed-forward equalizer and RX side AGC. This has been realized in 65 nanometer CMOS process. The PAM4 output driver with 2-tap FFE has been shown in this figure. The AGC has been realized with the source degenerated differential pair. The resistive degenerated resistors has been varied to get different gains from the AGC block. This figure shows the combined frequency response of the channel, the equalization implemented by the FFE, and the amplification provided by the gain block. The TX and AGC maintain roughly flat frequency response. From our analysis, a minimum of 44 dB linearity is required at AGC's output. This table summarizes the performance of the previous implementation. As we can see from this table, a significant power is consumed by the AGC block while adding noise into its output. The AGC block also introduces nonlinearity into the system, which degrades the target SNR. Now, we are moving to the proposed transmitter architecture. This figure shows the block diagram of proposed hybrid voltage mode and current mode transmitter with CTLE. The 2.5 GHz clock drives the PRBS generator. The PRBS generator generates D0 and D1, which goes to the output driver. The voltage mode driver provides large transmit signal swing, but it is limited by VDD VM. The current mode driver amplifies the input signal's high frequency content. But this implementation is not constrained by supply voltage, unlike feed-forward equalized embedded output drivers. The total transmitted signal is the summation of the output swing by voltage mode transmitter and the current mode transmitter. The left-hand side, a schematic diagram shows the simplified voltage mode and current mode hybrid output driver with CTLE. The voltage mode driver provides linear gain, whereas the current mode driver provides the equalization. This has been explained by the first equation. The right-hand side figure shows the transfer function of the output driver of voltage mode current mode hybrid with CTLE. The equalization can be characterized by the ratio of the pole position and the zero position. This has been expressed by the second equation. The left-hand side, a schematic diagram shows the proposed PAM4 voltage mode current mode hybrid driver with CTLE. In current mode driver, PAM4's MSB and LSB is weighted by ICM and 2ICM. The input to the current mode driver is reduced by the capacitive divider, and this goes to the input differential pair, so that the differential pair operates in the saturation region and provides the equalization. The source degenerated resistor RS and CS has been scaled properly in GM1 and GM2. The expression of the output transmit swing has been shown by this equation. The right-hand side figure shows the frequency response of the return loss. The return loss is less than -20 dB for frequencies less than 2.5 GHz. Now in this slide, we have shown the simulated results of driver performance with RC extracted parasitics. The left-hand side figure shows the frequency response of CMCTLE when the voltage mode part is given the data of D0, D1 both equal to 1. The CMCTLE can be adapted by changing the equalizer's zero location while compensating the different channel losses. The zero position can be changed by changing the degenerated capacitor value CS. The right-hand side figure shows the power spectral density when the CMCTLE has given input of differential sinusoidal tones. The simulated SNR due to nonlinearity is 43.83 dB, which is as expected. Now, moving to the measurement results part. This slide shows the half-duplex transmitter performance over 1 meter cable. The transmitter transmits 1.1 volt peak-to-peak signal, out of which 0.8 volt peak-to-peak comes from the voltage mode driver and 0.3 volt peak-to-peak comes from the current mode CTLE driver. The total channel includes 1 meter cable, package parasitics, onboard traces, and SMA connector. The left-hand side figure shows the received signal without any equalization. The right-hand side figure shows the eye diagram of the received signal with equalization when CMCTLE setting is 0, 1. The same thing has been shown for the 2 meter cable. The left-hand side figure shows the received signal without any equalization. The right-hand side figure shows the equalized received signal with the CMCTLE settings of 1, 1. This figure shows the die photo of the design implementation. Transmitter is designed in 65 nanometer CMOS process. It consumes an active area of 0.029 mm square. At 5 Gbps, the transmitter consumes 20.39 milliwatt power. The voltage mode driver consumes 4.64 milliwatt, whereas CMCTLE dissipates 14 milliwatt power. Other digital blocks and PRBS generator consumes 1.75 milliwatt. This slide shows the performance comparison of this work with the other state-of-the-art references. As we can see from this table, energy efficiency doesn't always provide the best figure of merit. Therefore, a separate figure of merit we have considered where the channel loss has been included into the equation. From this FOM, the higher the FOM number is, the better the transmitter performance. Therefore, our design performs better than the state-of-the-art implementation of reference 1. Now, we'll conclude our presentation with a summary. CMCTLE with full swing voltage mode PAM4 output driver has been proposed. The transmitter signal is not supply limited due to equalization. The received signal swing is large after equalization. It eliminates the requirement of AGC block in the RX front end. The hybrid PAM4 voltage mode current mode CTLE driver achieves an energy efficiency of 4.08 picojoule per bit. Thank you.
Okay, thank you, Shraman, for the presentation. So I will ask you just one question with respect to the swing that you mentioned at the beginning, which was one of the motivations behind the hybrid architecture. I just want to know that how the current mode part of the transmitter is designed based on the voltage swing. Even though it is current mode, but you will design it based on the availability of voltage swing. So then we start the next presentation. The next presentation is about an LDO design. And this is the capacitor-less LDO, which is designed for high bandwidth memory and with a driving up to 230 milliampere current. And I request Javed to proceed with the presentation.
Hello, good day. My name is Dr. G.S. Javed. I'm from Intel, and I'll be presenting our paper along with our co-authors, Miryala Chandrashekhar and Komal Deshmukh, on the topic a 0.009 mm square, 0 to 230 milliampere wide range load current output for a capacitor-less low dropout oscillator for high bandwidth memory parallel IOs. It's a long title. Let's go forward. A quick overview of our topic. We will go ahead with a brief overview of the LDO and its operation. We will focus in detail about the design challenges in having a 230 milliampere current load delivery. We will look at the layout challenges, go deep dive into reliability and power delivery, followed with the results, and we will conclude the talk. An LDO is basically a regulated voltage output for a defined maximum load current. What you have is you have a PMOS transistor in a negative feedback circuit with an error amplifier which takes an input from a reference and gives the output according to what is the analog circuit voltage that is present and what is the amount of current drawn. Here we have a resistive feedback network where which compares the two reference voltages that are present here, and the load current is modeled as a capacitive output along with some amount of resistance. The pass transistor here is a PMOS pass transistor, and it has its gate connected to the voltage supply using a decoupling capacitor. So what are the unique challenges that we see in 230 milliampere load delivery? First thing, it's the simple large load current which is present. This large load current causes a lot of problems, starting from the size of the transistor. What is the size that you have to maintain? And as the size of the transistor goes very large, for example, to the tune of 7,200 devices of unit size that you have to have. Now you will look at challenges like how do you do the layout of this pass transistor, whether you would use a common centered layout, how do you connect the drain connectivity for all these nets so that you have minimum IR drop, or how do you maintain the current delivery is one point. Second, the voltage input, that you have the power mesh, right? You will have unique routing congestion and top metal sharing issues. We will be looking at that. Then the inherent device capacitance, so it has a significant value and it contributes to the loop stability. It ensures that the pole shift will move to the leftwards. That means your bandwidth of the LDO will reduce. Further, you have the CGD cap, and this CGD cap also will introduce a secondary pole, and this pole also moves leftwards, and also it provides some amount of stability. So it has got, we will look at the intuition how it is. Further, we will look at the output power mesh, where you will have the output voltage delivery and also among the current delivery that you are going to look at. You will have a reduced MIM cap value. You will have a lot of routing congestion because you will have routing congestion both at the input and at the output, and you will have to clearly distribute and partition the input nodes and the output nodes and their various locations. And you will have to understand that the top metal layer will have sharing issues. So along with this, you will have important points to be focused on the gate connectivity. You should ensure that the resistance is minimal because you'll have long poly tracks when you're connecting, or when you have a metal connectivity, you will have to ensure that there's low resistance. The capacitance that is present needs to be optimized such that it is not impacting. If there are any antenna effects, because having a large poly and you will have large metal routes, so potential antenna problems have to be looked at. There is going to be noise at the gate because there is large gate size. Gate resistance is also there, so the noise contributing will be there. And you have to understand that a lot of poly via metal stacks will be available in the gate size. Since you have 7,200 devices, they need to be connected to the metal. The gate to metal connectivity will be there. So these are some of the important design challenges, and we will address at the end of this talk. You will see the summary of all the problems being addressed with this. An important point when we go into while looking an LDO, since it is a feedback mechanism, is what is the loop gain. And the loop gain stability plays a very important role in providing the right kind of LDO output current and the regulation that we will look at. So what are the factors contributing the loop gain? You will have the gain of the error amplifier and the pole contribution of the resistor of the output resistance and the load cap of the error amplifier, represented here by REA and CEA. Next, we will have the pole contribution of CGS cap. Then we will have the gain of the transistor device or the pass transistor, which is the GMP and ROP. And then it will come in a feedback factor. Since it is a unity feedback, we will not have a major contribution, but we will look at what are the possible zeros that could enter. The dominant poles are the output of the error amplifier, which is GM, the CEA and REA, which will fall one of the poles. The second pole is formed at the output, which is a combination of ROP, which is the output resistance of the LDO pass transistor, and the cumulative effect of the CGD and the CL cap, which is seen at this particular node. So these are going to be the two nodes. Now, how does the loop gain impact? The amount of the loop gain that will be there will directly correspond to what is the variation that is seen at the output load due to the amount of current drawn at this node. Also, what is the noise coming on the power line supply. These two are quantified as line regulation and load regulation. So we'll look at how this has contributed in the later part of this presentation. Now we will look at some of the details of the layout challenges. Before we go into the layout challenges, we can give a quick overview of how the layout of the LDO has been laid out. Here we have the driver circuit present predominantly in the center, which will take care of the current delivery and also the load current. If you look at the driver on the left hand side, all the left hand side is covered with the power supply decap, and the power supply decap can be partitioned into the output node and the input node. So the power supply decap for this would be the regulated output could be on the bottom side, and the input node decap could be the forward side. Now, if you look at, there are the bias generation circuits which are present to drive the amplifier, and the voltage references are present here. A discharge circuit is present as a circuit protection mechanism to ensure that if any residual charge present on the LDO cap, output cap, or on the LDO drivers will be discharged when the LDO is not in use. So a discharge circuit is present. And the feedback circuit begins here, where the resistive feedback and the error amplifier is taken from in this portion, in this blue position, where the negative circuit is present, and the input for that is given through the voltage reference along with the low pass filter, which is present to ensure that the perturbations present in the circuit which get picked up from the feedback point are captured here. So a low pass filter and the VREF circuit block are present here, and this is the entire layout. Now, if you look at the layout, they are designed in such a way that the feedback is voltage reference input is coming from the far right, and it enters into the negative feedback loop with the error amplifier into it. The output of the error amplifier drives the driver, and the driver output is given with the voltage supply decap present over here, and the output is given out through on the south side. From the north side of this circuit, you will see the power supply input coming into the LDO, which is the LDO input there. Now we will look at one of the challenges, which was the power mesh design. So the power mesh is present at both the LDO input and at the LDO output. When I say power mesh, I am hinting to this connectivity present on the PMOS transistor, both on the LDO output side and the LDO input side and the LDO output side. So here you have the regulated output, and here you have the LDO input, and where the power supply is connected. So the power mesh is for the metal connectivity at the power supply and the metal connectivity at the drain. So we will be looking at these two portions where the power mesh is used. So how is the power mesh designed? On the in the figures A, B, and C, you will see the top view of how the power mesh is designed. You can see they are designed as unit cells, and they are staggered in an example of 4x4 here, and it is fit into how the system needs it at that particular level. The power mesh is again stacked up with metal layers, and we see the metal layers are orthogonally placed, where one metal, if it is looking into the circuit, that is coming out of the circuit, then you will have the other metal in orthogonal in the 90 degrees place. So if one metal is coming this way, the other metal is going out this way. In this case, we will the importance is given to how the via, that is to be present between the two metal stacks, and to ensure that the power delivery happens right from top to bottom. This is crucial because to reduce the amount of IR drop that is present and to ensure clear delivery of current data. Now, important is the top metal layer have higher current density. That's why you would see they are fatter in size or thicker in size, and they have a lower unit metal resistance. The intermetal capacitance, the capacitance that can be formed, or the stray capacitance which can come up between these two metals, can be used to hold the current values and voltages, and this can act in power delivery. The parasitic can be reused as a power delivery aspect, and very careful via placement is to be taken care of to ensure power delivery from top metal layer to bottom in the power supply, and bottom to top. So both vias presence has to be taken care of for input and output power deliveries. An important factor comes in when you are delivering a large amount of current across a device size, and that comes into picture because we have 7,200 fingers of the input. Now, when you have this kind of device size, there is going to be large amount of voltage drop across this transistor. So, to avoid the max voltage drop, we have to take care of something called EOS, which is the electrical overstress. We need to ensure that the field that is present across the drain and source does not stress the device into higher limits. So to avoid that limits, we have to protect the supply. So what is the method we follow? Large VSD can damage the device and reduce the lifetime of the device. So the method that we follow is we will distribute the entire VSD across two devices. That way your stress on the first device is minimal, and rest of the device can act as a protection as well as to ensure that the flow is taken care of, current flow is taken care of. So what we do is we add a cascode device, a second cascode device of the same size that ensures the same amount of current that flows, and the VSD is now broken down into two devices. That way the stress on each of the devices is lesser, and this allows for even supply changes. So some amount of supply variation that you would see would get protected by this cascode device, and the variation would be lesser. This would include the load regulation that will happen, and also since you are going to have a higher gain because of this cascode, you will see better regulation, also protection from the line regulation that you see in the input. Now there is an impact that you would see because of this cascode. What is that? We will see an extra set of capacitance that is going to come, but now what we would see is the capacitance would now be transferred. The load capacitance would now be transferred to a CGD at this particular node from here. Without this device, this would be the initial place where the output node would be present. Now that output node is transferred to a lower place where the output node is present here, and it is from here that the output is drawn. The compensation caps that are present here would help in maintaining this particular device gain and a loop stability, and this will also impact to show what is the CGS that will come here and what is the pole or the far outside secondary poles that are coming. They would get compensated by the presence of these CGD and CGS of the cascode device present here. Now let us look at the results on how what are the proposals that we gave and how the results solved the challenges that we had in the device. So first thing we had to take care was effective error amplifier design. So the error amplifier had to be designed in such a way that it responds without any difficulty to the output change. So the current load that would come, that would get pulled from a 0 to 230 milliampere that was present here, that output load current should be your error amplifier should be able to support. Now in this graph we see that the error amplifier is able to support a range even from 1 milliampere to 200 milliampere. and the phase error also is given here. So what do we see as the gain margin, phase margin? The gain margin is we see as 5 dB between these two load currents, which is manageable and does not destroy, since we have the maximum maximum gain that we see at the DC to be greater than 50 dB. And the phase margin that we observe beyond the operational frequency of 1 megahertz, you see a phase margin of 10 degrees. And this phase margin is around the 60-degree phase. So from 60 to 50 degrees of phase margin is what we get. And this allows good error amplifier response at the frequency level, and also as a transient current load level, where tracking can happen and better feedback can happen. Next, we will stepping on from the load current. Now we will look at how the load is enabled. In this particular graph, we show that the LDO begins when we have an LDO load enable signal being asserted, and once this is asserted, the entire signal begins operating. As the load LDO goes higher, we need some amount of transient load current, or DC quiescent load current, that needs to be present. And this quiescent load current is taken care of in the leaker portion. So we have a leaker circuit which gives a finite amount of current to be present, and to ensure that the loop stability is maintained and it is not broken. So leaker is enabled, and this leaker enabled is in the microampere range. So some amount of current will go to ensure that the loop is stable and we are able to function. After the leaker gets disabled or deasserted when the operational circuits start to ping. In this case, we will have the uh, main delay line in the operation circuit for the clocking. So once the delay line gets enabled, the leaker gets enabled, which disabled, and this allows the stability to be maintained. So it is a make before break circuit. So first we will make or enable the MDLL, and only then disable the leaker circuit. Along with that, here we show a sample read, write, read condition, in which we take the cycle to how the read enable happens, where for one of the data reads of close to 175 milliampere, we are able to get the data read current. And for that particular data rate, we see that the amount of switching that happens is minimal, and this ensures that the load regulation is very good. And when we switch from 175 to 140, we have this transition. Again, there is minimal load regulation, or minimal load change, and showing effective good load regulation. Again, when you come back, we do not see that effect. We only see that effect when the LDO is disabled, and as the LDO is disabled, the output load voltage slowly discharges, and we have the discharge circuitry, which we mentioned, through which the discharge happens, and the current in the load circuitry is brought down to almost zero or to the leaker levels. So when the LDO is enabled, only then we will need the leaker to be enabled. When the LDO is not enabled, we can turn off the leaker condition. So this way we will maintain the loop stability of the system. This is a quick in detail discussion of how you maintain the load ripple. We see that when we apply a supply voltage of 1.1 volt and 100 millivolt ripple at 100 megahertz. So the frequency here is 100 megahertz, and the ripple that you see here is about 100 millivolt. If we look at the total output regulated voltage, which is the graph here in blue, so the regulated output for a 200 milliampere load shows a ripple of only 14 millivolt at the highest. So this shows that the output is significantly well understood, and the regulator output is set at 166 millivolt, which is close to 140 millivolt of dropout voltage that we see from the power supply, a 1.1 volt input to 966 volt or 140 millivolt dropout, and this is the amount of ripple that we see at 14.7 millivolt, which supports our really very good line regulation that we see on the power supply. At the load regulation here, like we showed in the last two slides, the load regulation here is shown that only about 3 millivolt of load regulation is observed for various input supplies, and as we transition the load supply from 34 milliampere here to 170 milliampere for the maximum load supply. So this is before the MDL can be enabled. This is after the read cycle in this particular test case. And we see that the rise time is about 13.6 milliampere in 10 nanoseconds, per nanosecond. And this rise time is defined at 10 nanoseconds. So within a 10 nanosecond period, a 3 millivolt disturbance is a sign of a good load regulation in the circuit. And this is attributed to having a good PS power supply rejection ratio, also having the good gain in the system, and also the presence of the cascade device, which further enhances the gain in the system. So all these three contribute to a better load regulation in our design. So quick comparison, we did not have too many circuits showing maximum load current range of 0 to 200 or 0 to 100. So we had one capacitance, one reference that we have taken. And if you look at our load range, though we are in the 0 to 100 range comparison for the 65 nanometer, since this was a 7 nanometer work, we are using the similar figure of merit and showing that it is functional at 230 milliampere also. And if you look at the input voltages and the output voltage and the analog architecture, they are similar in comparison. Now, the focus points that we would like to bring out is to show that the PSRR that we have, the power supply rejection ratio, is 32 dB at 51 megahertz, which is 5 times more and 5 dB higher than the comparison voltage. The delta V in millivolts that we see per load step, we see only a 3 millivolt increase for a load step of 135 milliampere, whereas this shows a 228 millivolt for 100 milliampere. So taking into factor the change in the design technology, we can easily say that if not for 10x, they can easily be a 5x betterment that we see in the load regulation that we see. The settling time is also 10x better, that we see that settling time happens in under 120 nanosecond that we see, whereas for this particular work, reference was seen in 2000 nanosecond was taken, or less than 2 microsecond was given as a settling time. So this allows for fast read-write times where you are able to switch, and also ensure that with the settling time you are able to reduce the latency of data transfer also coming from the power supply operation. So this is a reference work that is taken and given here. So in summary, the design challenges for current delivery were highlighted. Specific interest was shown on how the large device size was posing a challenge. So we understood what was the device cap, inherent cap, how it could contribute, what were the layout methods we had to follow to ensure that the large transistor size is going to be a benefit. We talked about what is the power delivery methods and the device protection methods using the power grid that we showed for device, and also how the cascade device can be used for device protection. The gate capacitance that was involved and how its loop stability was better, and we also showed results on how we got 5x better line and load regulation in this presentation. With this, we would like to summarize and show that these are the reference circuits that we have used for the design comparison. Thank you very much. I'll open for questions.
Okay, thank you, Dr. Javed, for your presentation. And I would like to ask you one question. So you mentioned the purpose of using the cascade architecture is to eventually protect the devices against the higher voltages, and also at the same time you said it is for enhancing the loop gain to provide better regulation. So how much was the breakdown voltage of the transistor? And because your voltages are anyway limited at the input also to around 1.1 volt.
So the breakdown voltage that maximum we can go, I think is technology limited, but it is greater than 1 volt. So we had to ensure that with the dropout voltage and that it can come out lower than what the limitations of the EOS voltages are present. I'm not at the liberty to give that number though.
Okay, so therefore the main motivation was protection or enhancing the loop gain.
Main motivation was protection. Loop gain was an additive effect.
Okay, and one of the audience members is asking, what is the delay line? This is the question, because it seems that you mentioned about the delay line.
Okay, so MDLL or delay locked loop is a circuit which is used for clocking the circuits, and it is essential in the high-speed circuit that you have for data transfer applications. So it's just a clocking circuit which allows you to ensure that clocks coming at the right delay phases, and you're able to get multiple phases to choose from this delay line. I hope that answers the question.
Okay, yeah, I think it was more about what is the full form and the block. And there is one more question about the impact of the actually very high gate capacitance that you have on the actual pass transistor and the stability of LDO. This was mentioned by you at the beginning, but it was not elaborated. So maybe now it's the chance to elaborate, which is response also to the audience.
Sure. So the inherent gate capacitance is actually pretty large. So we utilize that gate capacitance to do two functions. One, since this is present from the supply, since it's a PMOS, the capacitance exists between the power supply node and the gate of the pass transistor. So this allows to do some amount of filtering action. It allows to decouple the gate device with the source. Along with that, the after effect of it is the stability impact. Such a large device basically limits the bandwidth of operation of the LDO. It's a primary limiting factor. So that, along with the error amplifier, output load, and the RC that comes from the tracks, that RC typically controls the load capacitance and also the closest pole that is present. So primarily bandwidth reduction happens, and you have to live with it, but it also allows
sorry, I
greater
interrupt
stability.
you, but I think the question is that how did you ensure the stability? The question is how did you ensure?
So a lot of analysis went into the pole zero design, understanding where it is a limiting factor. First, we need to understand that 230 milliampere is an extreme condition.
No, so, that is okay. So maybe you can just tell that, did you add extra zeros? Did you, for example, change the location of poles? Finally, yes. Just qualitatively you mentioned, no need to
yes, we had, there was a zero addition required there, and by adding resistors in the path, you create an also slower path, so zeros is added.
You can mention where you added the zero.
I added the zero at the CTD gap where after the compensation comes in, so that it effectively reduces after the protection devices.
Did you add series resistors with the gate?
It was a series resistor with the gate.
Okay. Okay, and there is a similar question from another participant, but I don't repeat it because that's the same thing about the stability. But there is also one question, which is, of course, a very typical question. It is known, but you may repeat it again. So what if you replace PMOS for NMOS transistor? I think that is known. Okay,
that's it's a very simple thing. Now question appears in a different way. So right now your CGS will be, you will have a diode drop coming in or your VTH drop coming. You will have lower efficiency that you will have a current. So these are all standard questions, and I think the answer is well known, but these are the two main points I would like to highlight on.
Okay, but I think there is also a fundamental problem with NMOS transistors.
Yes, the strength is a little faster, so you will actually see a lot of issues coming from that side also. Yeah.
Okay, but I think the main reason is because of the functionality, but that's okay. I request that audience to get back to me. I will explain what is the reason for not using NMOS. Okay.
Thank you so much, Professor Maryam.
Thank you.
It's a pleasure. Thank you for being the chair. Thank you so much. A very good afternoon to all the participants.